Alright, so a lot of stuff to talk about. I hope that you all got a little bit of a start on this and came up with some problems. Let me go ahead and talk for a while, and then we'll open it up for questions. The first is that I have added to the project description, or the folder that contains that, another tarball. So there's this additional one, which is testing.tar, and the second paragraph talks about it. What it contains is it contains a bin directory which has some tools that'll help you test your project 3 and test the other projects for that matter. It also is going to extract a directory inside your P3 directory. So actually, let me go ahead and download these so we can just take a look at them real quick. Alright, so you had this one from last time, and that creates a source directory. So the testing tarball, you want to extract in the same directory you were in when you extracted this one, meaning before you extract the testing tarball, do an ls, and you should see the source directory sitting there, right? So when you extract the testing one, note that it's going back into source into P3, and it's creating a test directory, and there are a whole bunch of tests here. If you've had Tyson before, some of this may be familiar. I'll go over it in either case. And it also creates this bin directory. So once you extract this testing tarball, you'll see the bin directory next to source. And if you drill down into source, where the project stuff is, you should now have a test directory there as well. If you, let's see, let me go here. No, I did not go there. Alright, if I go down into the bin directory, there's a README there. So let's take a quick look at that, and you'll see, whoops, I gotta do it here. Alright. So in the bin directory, there are 3 executables, GT, VD, and VDE. This set of tests would be in that test directory in P3. And there's a script that was named GT to mean GPL test. And this shows you what the GT script does. Okay, each test file has an input file, an output file, and an error file. And in fact, if I come here and I do an ls, you can see that there is GPL would be the test GPL code. Output would be the expected output of your GPL executable and the expected error, right, coming out of standard out and standard error. So those have been separated into separate files. So you can manually run a test. What you do is you run your executable. You take this particular GPL file as test input, and then you redirect the output, and you redirect standard out and you redirect standard error into these 2 files. This is showing you precisely what GT does. You could certainly run it manually, and you could name these anything you want. There's nothing hallowed saying that you have to have a results directory and that you call your output t001.myout or likewise for standard error. The reason it's being shown this way is it's just explaining when GT runs, this is what GT does. Okay, and then GT does a comparison on the output your program produced with the expected output for the test, right? So all these here, all these out files are the expected output for the test, as well as the expected error output for the test. And then this GT tool will tell you which tests it passed and which tests it didn't pass. All you do is you run the executable and the output looks something like this. I think, with any luck, I got a version of GPL here with a bug in it. Now, it'd probably be easiest to get that binary directory in your path. I don't have it in my path, so I'm going to say up in my parent directory, there's a bin directory, and I want to run the GPL tests. Churns, 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 passed most of them. It didn't pass test 17. And now what I want to do is I want to see, well, why didn't it pass that? How is my output different from the expected output, and likewise for the error? And that is what the other two executables are in the directory, which are VD and VDE. Where does it say VDE? There we go. And VD will do a comparison of standard output files. VDE will do a comparison of standard error files. And it'll generate an HTML of the differences. So let me run. I'll look at the differences in standard output. They're both incorrect, so I can look at both of them. Sometimes only one or the other will be incorrect. And I want to do it on test 17. You're welcome to do it that way. There's a little code in there to let you remove the zeros, leading zeros, if you don't want to put them. And it does some churning. If I do an ls, let me do an ls-r. There we go. The most recently created file is this diff.html. And then you can bring that up in a browser. And this is the expected output, and this is my erroneous output for standard out. So this is saying there are no errors found, and when in fact it looks like there should have been errors. We can do the same thing for the error output. Oops, where am I? Here. When I run VDE, it's always going to overwrite diff.html. That can be convenient just simply because I can come here and just refresh the screen and get the new output. Alright, so that says that's a problem. What might be useful to figure out what the heck's going on here is to take a look at the GPL file for test 17 and see what in the world it was feeding me that it screwed up on. So I'll look at tests, test017.gpl, and oh, in this case there's a nice comment in there. If you use the regular expression like this in GPL, and in fact in my case I was using it for identifiers like variable names, right? Trying to get all characters from the uppercase A down to the lowercase z. The problem with doing it this way, and this is precisely what the test was trying to find, is, let's shrink that, uppercase A to lowercase z is going to start at 65 right here. Oops, that's an image. It's going to start at 65 and end at the bottom down here at 122. That's great. It gets all the letters of the alphabet. The problem is it also includes the glyphs that are between the uppercase Z and the lowercase a, namely the square brace and the backslash and so on and so forth. And that isn't what I wanted. I just wanted uppercase letters and lowercase letters. And so this comment here is basically telling me that I really need to change this to be this expression instead, and that will then not include all of the weird characters between the uppercase Z and the lowercase a. Okay. Then I fix that, and then I can go ahead and try running GT again. Note that when you run it subsequently, it skips tests that were passed, and so that just for being quick about it, so you can focus on the tests that failed. Not that big a deal here, but in some of the later projects there are literally hundreds of tests, and it can take a long time, so this is a nice speed them up to just focus on the problem tests. And if it looks like they're all working, then it's nice to go ahead and do this one more time with the all flag, which means it'll rerun every test even if it passed, just to ensure that everything's still passing, because you might have screwed up a previous test that had been passing before and making a correction. And so that'll force a rerun of all tests. Okay? Does that make sense? All right. So that'll hopefully help direct you to getting the project done. Let's look a little bit at, just one side note, if you're comfortable in Vim, if I go up here and look in the bin directory and I look at either of these, either VD or VDE, down at the bottom here's the actual command that's generating the HTML file. It's running vimdiff. If you're comfortable in Vim and like hanging out in vimdiff, just comment this out and uncomment this, and it'll actually throw you into vimdiff rather than generating an HTML page. So for the Vim junkies, there's that. That reminds me of another note. On the gpl.y file that was provided, there was stuff. There are a couple percents, there's more stuff, there are a couple percents, and then the productions go here. And I got into the file a couple evenings ago, and I threw in a production, and I wasn't getting syntax highlighting. And after a lot of head scratching, it turned out that there was an extra space in one of these. Must have been this first one. So this is showing ends of lines. You'll note that there's an extra space right here. When there was an extra space on one of these, I don't remember which one, it was causing all these productions just to be plain black and not be nicely syntax highlighted. So if you're a Vim user, double check these double percents and make sure there are no spaces on the end of that. If you eliminate that extra space that's in one of those, then these should be nicely highlighted after that. Okay? At least on my version of Vim, I was having that issue, so I throw that out. All right. So looking at the assignment a bit more, I wanted to talk a little bit about what the assignment description said about shift and reduce errors, and also about precedence. We haven't talked very much about those things. I've got somewhere, all right, I've created a very simple so this is the flex file. It takes integers, it can handle addition, and it can handle multiplication. and then we go ahead and don't do anything for the other characters we might get. I look at the Bison file for the parser, and I've got my tokens declared here for the integer, for add mult, right? These are the things that are going to be returned to me. And I've specified precedence here. I want to work backwards. I want to look at this thing working fine, and then we'll break it and see why it's broken. So there are two pieces of information being provided for each of these. The first is the word left or right, and the left or right is referring to the associativity. This is going to reduce down to 9 plus 8 plus 9, and that's going to reduce down to 17 plus 9, right? So what's happening is when you're confronted with two of these operators, two of these addition operators, you resolve it, you resolve the left one first. So that's what that's referring to, that left associativity. The order that these appear in the file is specifying the precedence level. So the sooner you see them in the file, the lower the precedence. If they have the same precedence, like if I was dealing with subtraction as well, those would have the same precedence level, so I'd put them on the same line like that. Okay? That gets you most of the way there. There are a couple odd ones, and one is subtraction is left associative, so you put that there. But that isn't the only case where we see subtraction. We also see, or where we see the, I should say the hyphen, the minus sign. We also see it as bound like this, right? And this precedence is a lot higher than this precedence here. Yes? Meaning that if I'm going to do that, I figure out the -4. I turn the 4 into a -4, and then I subtract that -4 from 5. If you look at it that way. Okay. So what I would do is, since this operator is a lot higher than the regular subtraction, way down here at the bottom, I'm going to say that it's non-associative. So if it's associative, I can have a whole bunch of them chained together. If it's non-associative, I can't chain them together. That's nonsensical. What's actually happening is we have -4, and then we're subtracting 8, and then -3, that kind of thing. Well, it doesn't work to specify this unary operator here because we've already used that token, T sub, and that just confuses the parser. Well, what do you mean? Do you want it to be way up here or way down here? So what you have to do is you have to actually make up a totally different token. And I don't remember, I think it's talked about in that write-up. What was it? Unary. No, I don't remember precisely what the token was. It can be called whatever you want. Then you have to go down to the production. So let me actually come here. I already have that downloaded, so let me oh, I should have that there. Let's see what they call it. All right, so they call it, he calls it unary ops here. You can call it whatever you like. Then what you have to do is you have to go to the various rules, the production rules, and you have to say it's this rule here that has this precedence, this really high unary binding precedence. And if we look at this, what is it, T minus. So there's the binary version. That precedence was specified way at the top right. It said % left, T minus. Here, this expression has to have a different precedence than this. This has to have that much higher precedence. So what the technique that they've come up with is you say, I want this specifically to have a precedence that is the, now I've forgotten what it was, this one, unary. So that's how you get around having different precedents for the same symbol depending on how it's used. There's one other that's very common, which is the dangling else. So you have if statement, else statement. Let me put this in the device stuff. So an if statement by itself can reduce down, and we'll talk very specifically about this idea of reduction. But in essence, if you have something like this in your code, that gets reduced down to a statement. If you have something like this in your code, that gets reduced down to a statement. Well, the problem is, what if you've reduced this down to a statement, and then the way the code looks is if statement, if I guess what I don't have in here is the expression. And the question is, does this else actually tie to this if here, or does it tie to this if here, right? And you have to, that same precedence trick we used for the unary operator, you also have to do for that if else. That's the only other case where you have to use it. You know, the easiest thing to do is just do a little Googling, type bison dangling else or something like that, and there's 1,000 ways of solving the problem. Just pick one, and they lay them out pretty well. All right. So what's happening with this whole shift reduce thing? So looking at this, I can read this, I can read in, I can do addition, multiplication. I also have, where do I have that up? Here on the parsing, I've said precedence. Addition is a lower precedence than multiplication. How do you resolve them? There are a lot of operators in G. Huh?
What do you mean by, like, because you put left, you put multiply below add?
That means that the higher up, the sooner it comes in the file, the lower the precedence. I'm sorry, what, am I not answering the question?
I don't know. I don't understand what that means.
That just simply means if I have 5 plus 4 times 5, what do you do first, the addition or the multiplication? you do the multiplication because the multiplication has a higher precedence than addition. So what I have to do is I have to have these specified in the order of precedence, with lowest at the top, and as you go down and specify these, the precedence gets higher. Now there are a lot of operators, and you may not have memorized what the relative precedence is. All you have to do is go to Google and type operator precedence, and you'll come up with the table here. So like all these here, there's some subset of, which ones? Yeah, these. These here are part of GPL. All of these would be on the same line. Do you say percent left or percent right? They're all percent left, but that's what this column is telling you, the associativity. So you just use this to go ahead and rank them, and then it's just real easy. But note that the order you put them in the Bison file is opposite for how they're listed here. So lowest precedence is at the bottom of this table, but that means these have to be the first that appear in your file, right? So it's going to be an exact reverse as far as this table is concerned. All right, so I specified the precedence. Again, we'll look at the ramifications of not doing that and the impact on your code momentarily. Very simple. All I do is, we've talked about the start symbol. We'll talk about it again, but let me start down here where I can have an expression. If I have an integer, it can reduce to be an expression, or I'll just say EXPN. It can be reduced to be EXPN. Or if I have two EXPNs with an add in the middle, that'll reduce to an EXPN. Or if I have this, then that'll reduce to an EXPN. What am I doing in each case? Again, the $$ is what the result would be, meaning this right here, if I was going to do what I'd refer to as a reduction. If I'm going to reduce tint to EXPN, I'm going to take whatever's in tint, that's $1, this is $1, this is $2, this is $3. That's $1, that's $2, that's $3. This thing over here is always $. So if I'm successful in finding a tint and I'm going to reduce that to be an expression, then I'm going to assign whatever that semantic value is for that integer to EXPN. Why do I do that? Because when I get here, I'm going to have some value in EXPN, some other value in EXPN. So what I'm going to do is take those two values, multiply them together, and that result I'm going to assign to whatever it reduces to. But let's look in detail about this this whole idea of reducing. Sure I've got, okay. Let's do a quick run of it. Flex, Bison, oh, I'm sorry, Y. So that's all it does. Very, very simple. And I could chain those together as long as I wanted. All right. So this whole idea of parsing works on the idea of a stack. Our lexer, our scanner, is reading in the raw text, our GPL code, and it's converting them into tokens, and it's returning those tokens to our parser. So all the parser sees are the tokens. So if I type this in, the scanner, the lexer, is going to convert those into what we see here. And what I've done is in parentheses here, I put what the semantic value is. So this is what the parser sees. The parser maintains a stack. And when everything begins, the stack is totally empty. And this dot, and you'll see this notation both in the literature as well as you can get Bison to create some input that does this as well. This dot always represents the current position of reading in tokens, and whatever you have to the left of the dot is on the stack, right? So if I wanted to move this thing onto the stack, I'd basically move that period there, and graphically that means I have one thing on the stack and all this other stuff is still yet to be read. Okay. There are only two actions that I can take based on the grammar rules that I've written. I can either shift the next item to be read in onto the stack, or I can take a bunch of stuff that's on the stack, find a matching rule, and reduce it. So that means that if my stack has an EXPN, a TAD, and an EXPN, I then am able to pull those three things off the stack and reduce it to just that. That's what the reduction part of it is. Okay? So the first thing is there's nothing on the stack. What we're going to do is, I've even written it here already, we're going to go ahead and do a shift. And when I shift, all I do is I take that tint token, and it has a semantic value tied to it, and I've shifted it onto the stack. Now, the question is, do I want to shift and put both tint and tadd onto the stack, or do I want to reduce this to something else? And if I look back at my rules here, the question to ask is, let's say for the sake of argument, I do a shift. Let's pretend I do a shift, and now that's on the stack. The question is there anywhere in the grammar that does something with a tint followed by a tadd? And if I look here, the only place tint, here's my grammar, right? It's quite simple. It's not the hundreds of lines of GPL, but the only place tint appears is here. There's nowhere in the grammar where I would have tint followed by tadd. No such rule exists. So if it would be wrong of me to do a shift. So the next question is, can I do a reduce? Given what's on the stack, is there a valid reduction that I can do? And yes, there is. If that's on the stack, I can reduce that to EXPN. And what am I going to do when I reduce it to EXPN? I'm going to take whatever's in that integer and the semantic value for tint, and I'm going to shove it in to be the semantic value of EXPN. So I'm going to do a reduce. Let me move this a little bit. Actually, I want to copy this before I write that. All right. Do a reduce, and now this becomes EXPN. So now, what is the next thing we're going to do? Is there anything, and then the final piece of the puzzle is that this type of parsing is called a look-ahead parser. Before it makes a decision, it knows what's on the stack, obviously, because it's read everything in to that point. It has the ability to look ahead at the next token before deciding whether it's going to reduce or shift. Okay? So it knows it has EXPN, and it knows it has a TAD coming up. And the question is there any valid reduction of EXPN if an add is going to be next? And we look at these rules. Well, here's an EXPN, but there's no add that would come after it, so there's no way I could end up here and reduce to some start symbol. So that's going to be invalid. However, I do see a rule where if I already have an EXPN, if I bring in an add onto the stack, I'm on my way to completing this rule. So shift is the right thing to do. So I'm going to shift, and now I've got.
Why don't we, like before, why don't we just not look ahead and just put EXPN into some start symbol? Because we didn't look ahead with the T.
If you put, so let's say you put EXPN into the start symbol, then you've got what your pattern is start symbol plus what follows. And there's no valid rule to take, right, your valid rules are the things, here are your valid rules. This is a valid rule, this is a valid rule, these three and EXPN after the colon here are your valid rules. Nowhere do I have a rule that says, so I have whatever here, do I have a valid rule that has some start symbol, whatever follows. What are we looking at? Right, that rule doesn't exist, so I can never do that. I can never have that on my stack.
But we had T-ins.
Yes.
And we had just T-in.
Yes, but we don't. We also know that we have other things that need to be read in.
Yeah.
So, one thing that's valid then is if rather than having 3 plus 4 plus 5, that's all my input was. That becomes T-int. There's nothing else to be read in, so it's going to go ahead, and there's nothing that could follow T-int, so I have to reduce that to expression. There are valid things that could follow expression. I could have the addition operator follow an expression. I could have the multiplication operator follow an expression. Or I could have nothing follow the expression. And if nothing follows it, then I can do that reduction to the start symbol.
So are we looking ahead when we reduce? And
We look ahead before making the decision to whether we should shift or reduce.
So, but on line 3 here,
Yeah.
are we looking ahead and seeing that we have a T-add and knowing that we shouldn't go from T-in to expression to start symbol?
It should the way it should be in a state where it's able to reduce without the look ahead because it's unambiguous. There's nothing that can follow T-int that's valid. If I have T-int in anything, that's invalid and illegal.
Okay, gotcha. Because yeah, but so then with the expression, because there's multiple ways it can be evaluated, do we look ahead?
Absolutely.
Okay.
Yeah. All right. So now we've just done a shift, right? We did the shift shown here. That's moved that period, which shows that we now have two things on the stack. And then the next, I want to follow my notes just to make sure if I fly by the seat of my pants, I'll make a mistake and have to back up 3 rows down. I've got EXPN and add, and I have an int coming up. First I see, is there any valid reduction to just take EXPN and add and reduce it to something? No, there isn't. This is the only thing that involves add, and it actually has 3 items, and all I have on the stack are 2 items. So there's no valid reduction in my grammar, so my only choice is to shift and see what happens. So we go ahead and do a shift. I wanted to copy before I do that. We do the shift. Now we've got 3 items on the stack. At this point, we have T-int, and we kind of repeat what we did up there on the second line, which is there is no rule in our grammar that allows anything to follow in, right? If I shift, I've immediately broken my grammar. So the only legal thing I can do is to reduce T-int down to an expression. Here again. Now we've got a bit of a poser, because what we have on our stack is EXPN, T-add, I'm sorry, is it EXPN or EXPR? I've been screwing this up this whole time. EXPN. expression, tadd expression is on the stack. Is there a rule to allow me to reduce the stack? Yes, right here. Or, sorry, it's addition, right? Yeah, okay. This one right here. This is a valid rule. I can reduce the stack and replace this, do this magic right here, and then reduce to this. And the way that, if we were to do that, the way that would look is I would just have expn. I would do the 3 plus 4. That semantic value is now 7. And then I would be sitting with this stuff on the stack, right? But I look ahead and I see, oh, I've got an expression sitting here. If I read in molt, I also have a valid rule coming up. If I've already read in an expression, and it would be valid for me to shift molt, because I might be able to match this rule here. This is ambiguous. At this point, normally, the grammar breaks. And this is what's called the shift-reduce problems that are mentioned in that project write-up, because it's ambiguous. Do you reduce what's already on the stack, or do you shift something onto the stack? Because both are valid. Both go down valid rules of the grammar. That's where lines 15 and 16 in your Bison file come in. We're saying if you're confronted with either doing the reduction involving add or doing the shift because of the molt, you choose the shift because of the molt because it has higher precedence. So there's no ambiguity. So we go ahead and do that shift.
So it looked ahead there.
Yes, absolutely. It had to look ahead. Yeah.
Why does it have to look ahead? We have a valid like statement on the stack.
Because the look ahead gives our grammar more power. You would be unable, if you didn't have look ahead, you could not do this arithmetic. Or excuse me, I have this arithmetic wrong. I want to do this. Oops. That's what I meant to have up there. All right, I need look ahead to be able to do operator precedence.
So every statement here really should be the parser's going to look ahead at least one.
Yes, and by definition, it only looks ahead one.
Yeah.
And so this is something that we're going to be at a certain point getting more theoretical in class, and we'll look at different parsing strategies. And so this is a very common, popular one that Bison has implemented that lets you represent essentially nearly anything you could think of for a programming language, since that's specifically what it's catering to.
Is this a job we could only accomplish by setting precedences, not by restructuring the grammar?
In some cases, you could restructure the grammar. In other cases, it'd be unavoidable. So we've shifted that, and again, we still have something valid that we can do, right? We're in the middle of this expn molt right there, and since I'm able to possibly meet this rule, I should do another shift and see where I end up. Now I'm here, and again, I have nothing else to read in, so now all I have left is the stack. We do have a rule to convert tint, to reduce tint to expression, so we do a reduce. That becomes an expression. We have a rule that allows us to reduce expression t-molt expression. So that reduces. Oops. And then we have a rule that allows us to reduce expression to add expression. Which is our we're not done yet. Is there anything that expression by itself reduces to? Some start symbol. And the action I put when you actually do that reduction, the code that I run is to print whatever is in $1, which is this first thing right here. So this thing becomes some start symbol, and then I'll just say 23 to see out is the action that occurs. Now I'm done. So that's what these grammars do, is they all reduce down to the start symbol. And if you have some sort of error in your code, then that won't happen.
Can you go back?
Yes?
So like on, say, line 10, is it like popping expression 5 off the stack? And like it knows you can evaluate expression 5 to some start symbol, but because there's stuff on the stack still, it then
Yeah,
pops.
those are popped off the stack and replaced with the reduction.
Yeah, but so it's, say like we've reduced to line 10. To get to line 11, where we have the expression, is it like going through and checking the rules?
It actually what it so it ends up creating, the parser creates this huge state machine, and so it just depends on what state it's in. It's in a state where it knows, okay, now I'm able to go ahead and reduce this all the way and pull those off and put its reduction on. So it's a matter of what state it's in is how it's determining that. And so let me actually show that. I can run bison. We've been doing the -d option. It's V for verbose. And it creates the same name here with an output extension on it. If I look at that, it gives us information on the grammar. This is the stuff it's reading in, terminals it finds, non-terminal like EXPN and some start symbol, state 0, state 1, state 2. Note there are periods throughout here. If I'm in state 3, that's what I got on my stack, that EXPN to the left. And what can happen? Either there's nothing after EXPN, in that case I reduce here, or there may be a t-add in the look ahead, or there may be a t-molt on the look ahead. If there's t-add on the look ahead, I do a shift, and now I go to state 5. If there's a t-molt, I do a shift and I go to state 6. Otherwise, I'm going to do a reduction using rule 1, which is take start symbol. If you screwed something up, like let's say I don't put these, and I run bison, I get the warnings about shift reduce conflict. So the shift reduce conflict, it's a conflict because it's ambiguous. That means I can either do a shift or a reduce for a particular state, and I don't know which one to do, right? And if you open up the wrong one. Up here at the top, it'll tell you which state have the conflicts, so I can race down here to state 7. And this is the situation in this state. I've got EXPN. In this case, I have EXPN sitting on the stack, or I've got EXPN add EXPN sitting on the stack, or I've got, and with the appropriate look ahead, right? With no look ahead, with tadd on the look ahead, with tmult on the look ahead. Well, if it's a tadd, what I can do is I can go ahead and do a shift and go to state 5. That would be this one, right? We do a shift, tadd goes on to the stack, and now I race off to state 5. However, I can also do a reduction based on the second rule here. So I've got the ambiguity here. If I have tadd, either one of these could work.
So when it says tadd here, it means tadd's either on the stack or in the look ahead?
Right. So this is saying if I have EXPN on the stack and tadd is ahead, then I can do this. I can go ahead and do a shift to keep pursuing this rule. Or if I have EXPN, EXPN, and tadd is on the stack. Note in both cases, tadd is on the stack, or excuse me, tadd is what we anticipate being next.
Wait, so on rule 2, on the second one there, we're anticipating another tadd?
It could be anything. It could be anything. But if it is a tadd, it would be valid to reduce by rule 2. So I can either reduce based on rule 2, or I can do a shift based on what, I'm sorry, it has 2 twos. Based on that first rule, I could do a shift and that would be valid. So a shift could be valid based on that first rule, or a reduction would be valid based on that rule that's where the cursor is. So that's the ambiguity. And the parser doesn't know which one you want. So it has to be all deterministic. You have to make sure that everything for the same input, you have the exact same output. And you will know, so the tests are designed such that if you don't have your precedence stuff set up correctly, you'll get these kinds of errors. So hopefully that fills in some gaps on how to get the project done. Are there any other questions at this point? All this stuff, the example grammar stuff, that walkthrough of the shift and reduce, all that stuff will be posted with the daily diatribes you'll have access to. Yeah. So looking at where's it going to be? No, yeah, that should have been there. Let's see. All this stuff?
Yeah.
One big copy paste. You do touch it because of this unary, or excuse me, not that one. That's the binary. Here's the unary, right? You have to specify that this has a really high precedence as compared to line 241. So that's what I talked about earlier, how you have to kind of, since you have 2 different precedence levels for the minus sign, depending on the context it's used, you have to make up a token for one of them. So typically you take line 241 and you just say % left t minus, and then you make up a token for this one, and you say that this is, the precedence of this one is my made up token.
Which means it'll be like evaluated first, right? Like it has a higher precedence.
Yes, as long as made up token has a higher precedence than the one you specified for the minus sign,
Okay,
then
so because it's below the left.
because if you read from top to bottom in the Bison file, you find it lower.
So it has a higher precedence.
That's right.
Gotcha.
And it removes the ambiguity, right? Otherwise, 3 minus 4 minus 5, there's some ambiguity as to what happens. Also, I think the other thing, remember that the key is non-associative. Oops. So that means that if I made if I made addition non-associative, then that would be illegal. You couldn't do that if you didn't have any sort of associativity. And that makes sense that you can't do that with negating a number. I mean, don't think of computers, just think of algebra. What is that? What's -4, -5? Well, there's no operation there. You have two negative numbers just hanging out, right? It's non-associative. You can't have 2 of them or 3 of them or whatever in a row.
So what keeps the parser for the Bison from going and seeing that t minus expression has a higher precedence, and so then it evaluates this as 3, -4?
Because so you're asking, well, why does it not make the mistake of doing that?
Yeah.
Because because there is no rule that takes a t integer constant followed by whatever the result of negating the 4 is. Right, because that gets to this. Don't think about computers. What is that in algebra? Well, I don't know. That's 3. There's no operation there. You're not adding them or subtracting them or dividing them, right? It's broken. So that's why it doesn't do that. There's no rule that allows that. So the only possibility is to consider it a binary operator.
So how would it go through? It would C3. It would
That'd be a
convert that to an expression, right?
So the T3 would be an integer constant token, the minus token, another integer constant token, and then there's a rule to reduce that. It would look ahead to the minus, and it'd go, oh, do I do a shift because I want to do hope that 4 minus 5 is coming up, or do I want to reduce 3 minus 4? And it looks to what you specified. You specified that it's left associativity, which means that you always, in a chained expression like this, do the left hand, you do it the leftmost one, right? So when you're in algebra, you never say 4 minus 5 and then 3 minus -1. You always say 3 minus 4 and then -1 minus 5. So that's the associativity that you're specifying in the precedence. You're killing 2 birds with 1 stone, essentially.
Okay, I'm just trying to work through how like it goes through the rules to like not hit that point.
It would do a shift. It would do a shift. We're sitting there. It would do a shift again. So now we're there.
Oh, and then it would never go because we have expression, t minus expression, not just t minus expression. So it could not match up with this rule.
Right, right.
Gotcha. Okay.
And so that's what those states are. You end up with just a ton of possible states where it ends up, right? So it knows exactly what's going to be legal for the next thing coming up and whether to shift or reduce. And so that's one of the things that then we'll also do is we'll look what is the algorithm to get from what we're seeing on the screen now to those bajillion states. And you end up with this huge table. If you're in state 1, you do this and go up to state 5, and then there are gaps in the table, and those gaps represent things that are illegal that you can't do. So that's that. Any other questions? Yeah.
So if you have like 5 minus -5, how would that get evaluated? Would that be like 5, and it would throw the minus on the stack, and would throw the next minus on the stack, and then it would have,
and it would see, it looks ahead, so we're here, it looks ahead and it sees the minus sign in the look ahead, and there's nothing to reduce because there's no valid reduction on the stack right now. However, there is a possible rule that if it reads in another minus sign, it will possibly do a correct match of an upcoming rule, which is a minus sign, a unary minus followed by a constant integer. Now, is it possible that it isn't? What if it was like the word for here, for like a for loop? Let's write that dots on the stack. Well, that's entirely possible, but what's going to happen is at this point in time, there's nothing legal that can be reduced on the stack. It is legal to look ahead, see that minus, and say, aha, we might have a minus and a number after it. So it goes ahead and it pushes that onto the stack. And now it still has no legal reduction, so it's going to look ahead. The only possible legal thing for it to find on the other side is a integer constant, but instead it's finding some funky keyword. Right there, that is what you all know and love from 111, a syntax error. You've broken, that's not in the grammar. And that's why when you compile, especially in 111, the compilers are getting better. But for a long time, the compiler, you compile something, and it says there's something wrong on line 12, but the problem was that there was a semicolon forgotten on line 11, right? Up to that point, it's reading in fine, the grammar, it reads in the next token on the following line, and that's where the grammar gets broken. Any other questions? Definitely, I think definitely what you need to do is, now that there's kind of a bigger picture painted, to pound hard on this, so that over the weekend on Piazza and then on Tuesday we can try and get through any final issues you're having on it. All right. Okay, then I'll go ahead and stop right here and get this stuff posted for y'all.